Yes, and the first speaker of the conference is Professor Reimer Kühn from King's College. And please, Reimer.
Thank you very much, Mathieu. Thank you, the organizers, Mathieu, for having me here. It's a great honor and pleasure to be here. I fondly remember the last conference, and this is a Freudian slip, so the date of the last conference is still on this old talk because I used some of the slides. But this is the only remnant, or, well, not the only, some of the methodology is actually related to that talk. So this is about search and network exploration. So think of a network. Here is an example. It's an old version of part of the large-scale structure of the internet. And imagine that what you want to do is send a web crawler through this network structure and measure if this web crawler takes a random walk through this, how many different sites it will visit in n steps. That's network exploration. The other question we will be interested in is search. So imagine there are some of these vertices in the network have special items hidden on them. That could be malign software, that could be a secret which some villain has stashed away, and you are the police and wants to find it. So knowing nothing, you randomly search around. Will you find it, and how many of these things will you find in n steps? So that's basically the setup of what we try to do. So. Okay. Now it's frozen. Good procedure, much. Okay. Okay. Just this and this. Yes.
The arrows. The right and left. Okay. Yes. Okay. So here's the structure of my talk. I will tell you just in a bit more formal terms what can be said about exploration and search, and the theoretical side is based on a paper some 4 years ago by Katarina De Bacco, Peter Solich, and Satya Majumdar, who evaluated the number of different sites a random walker visits in an n-step work on complex networks. And I will basically run you through the formalism of that and tell you how we will sort of adapt that to our problem, which is search, and then describe how search efficiencies are actually evaluated, and that uses some message passing, cavity method, and some non-trivial steps to do the limiting theory there. And then I will tell you about results and compare simulations with what we find. So exploration and search, as I mentioned, the goal is to evaluate exploration and search efficiencies on random networks. And I will measure search efficiencies actually by the average number of different sites a random walker will find starting at a given site in n steps. And if I'm thinking of search, then I'm thinking of the number of sites which have an item on it, and I will give this indicator variable site j is 1 if there is an item on it, and 0 if not. And of course, if there are items on it, they might be put there by a hider, and that hider might himself or herself have a strategy doing that. So, which are correlated or uncorrelated with properties of the networks. And you can use this formalism to assess efficiency of, so the exploration thing, assess efficiency of diffusion spread of information. And we will do this for random walks, and not just for unbiased random walks, but also for large families of degree biased random walks. You can
use this to locate viruses in some computer or computer network or peer-to-peer file sharing network. You can use this to assess efficiency of web crawlers. So web crawlers, Google sends web crawlers all the time through the internet. They try to locate documents which have a search term in them, and if this document web page has a link to some other document, it follows links randomly, and by that fact Google measures all the time the importance of documents with certain elements in them. And you could ask yourself, well, are there strategies to improve that perhaps? I mentioned already that the hider might have bad intentions. So in the search context, there's definitely also a game theoretic aspect. You might pitch search strategies against hiding strategies, but I will not touch the game theory side of things in terms of Nash equilibria in any deep form. So let's come to the problem of different sites, number of different sites. What do we know? It's mainly, and I will be interested in the case of many steps, and there's a lot is known for d-dimensional lattices and for beta lattices, and that starts actually with work of Dworecki and Erdős in 1951, Vineyard 1963, Motrol-Weiss and Hughes and Sahimi for beta lattices. So what do we know? In d equals 1, the number of sites visited by a random walker in n steps grows like square root n. That's basically a measure of diffusion. It is almost linear in n, in d equals 2. And it's linear in n for dimensions larger than 3. And that is, of course, related to the fact that these random walks are either transient or recurrent. And the beta lattices are like d-dimensional lattices with d larger than 2. It's proportional to n with a constant b, which is related to the mean degree of the degree of the beta lattice, c minus 2 over c minus 1. And obviously c has to be larger than 2, because if c is equal to 2 for a regular graph, it's basically a large loop or a collection of large loops. So then we're down to the one-dimensional system. So for random graphs in the configuration model class, that's a work of, I was referring to, Debacco, Majumdar, and Solich. They found that the number of sites a random walker visits is proportional to n, so it's not just for the random regular graph or beta lattice, but also for random graphs in the configuration model class. And this coefficient b depends, of course, on the graph type. So they were able to do this calculation for large finite instances using message passing ideas. And it turns out that so much of what they have done will basically utilize here. So this is really an epsilon addition in some sense. There's another 2 epsilon addition to what they did in generalizing what they did to the thermodynamic limit, which turns out to be less trivial than in other cases. Let's put it that way. So how is this problem approached? So this is the first couple of slides. Now basically follow Debacco and Solich and Majumdar. And I should say that in turn is in similar ways already in the papers by Motrol and company. So they express the number of sites visited by a random walker at site in terms of probabilities, the sum of probabilities to visit sites j starting at I at least once in n star. So hij of n is the probability of visiting site j starting in I at least once during the n first steps of the random walk. And then you decompose hij
in terms of the times of the last visits m. So if the last visits at m, then that's the probability in an m-step walk to get to m, and qjj of n minus m is the probability of not visiting it again in the final steps. Now this is a convolution, so it's clear that you use generating functions in order to express that in terms of the Z transform, and there's a little bit of a model up here. So this equation in a Z transform is just the product of Z transforms, and so that's the Z transform of this one-step transition matrix, and Qjj is the Z transform of this probability of not visiting, not returning to a site that you have visited in n steps. Now these Qs are related to first passage times. You can convince yourself that the difference of qjj n minus 1 minus qjj of n is just the first passage time of returning to your site in n steps. And if you do the Z transform of that exploiting the convention that, I mean, that's a convention that you put fjj of 1, fjj of 0 to 0, then this results in this equation for q hat of z, qjj of z, is 1 minus fjj of z divided by 1 minus. Now, the f and the g again are related in this manner. This is just the Chapman-Kolmogorov equation in some sense. And so you can exploit that to express the relation between gjj of z and fjj of z. So you get this equation for the hij of z. So it's related to the ratio of gij of z and gjj of z. And so then you put everything together, you get the z transform of this quantity, of the z transform of this quantity of how many sites do you average in n steps. You z transform this, do the z transform of this n-dependent function. You get siz of siz, and this is the result. And then the large n behavior is extracted from the z goes to 1 asymptotics of this quantity. Now clearly what you need in order to evaluate siz, si hat of z, is the knowledge of the resolvent. If g hat of z is exactly this quantity, because it is related to the z transform of this resolvent, and we will consider transition matrices which are of this general degree biased form. It's not just Cij over the degree of the starting value vertex, but it's Cij times the degree of the target vertex. For instance, a function of the degree of the target vertex, S of kj. So the probability of transition to j is proportional to some function of the degree of the target vertex. I write this as little s, because the little s will refer to a search strategy. So this is and then, of course, normalization requires that the gamma I is just the sum over j, Cij, S of kj. So that makes W a stochastic matrix, and theCij's are the matrices of the elements of the connectivity or adjacency matrix. So the elements are 1 if sides are connected and 0 otherwise. And I should say at the outset that what I'm doing is restricted to symmetric networks. All this could and should possibly, for practical purposes at some point, be generalized to directed networks. And the techniques are available in some sense. It's just, as Melville von Samuelsey famously said, oh, cash, strength, time, and patience. I haven't been able to find the time to do it yet. So now, to analyze the Z transform of the n-step transition probabilities, so we have to evaluate this
I will call it resolvent, although normally the Z is in front of the unit matrix, but let's call that object resolvent as well. It's related in simple ways to the standard resolvent. So this is what we'll have to analyze. And in order to do that, we should note that the transition matrix W is itself not symmetric, but it satisfies detailed balance with an equilibrium density, which we can easily guess. It's gamma I S of ki is the left eigenvector of this W matrix for eigenvalue 1, and so it's the equilibrium distribution, and the y is just the normalization constant, so that sum over pi I equals to 1. And we can use this aspect as generally in cases where we have detailed balance. Although W is not symmetric, it is essentially symmetric by performing on G this similarity transform with a diagonal matrix, which is just which consists of the gamma ISI of the equilibrium distribution. And so G is itself similar to the matrix R hat, where R hat involves the symmetrized version of the transition matrix, and that is manifestly, you can convince yourself that it's manifestly a symmetric matrix, and we have all the tools of spectral theory for symmetric matrices available, which is a bit simpler than the one for non-Hermitian matrices. So, and then to extract the Z goes to 1 limit in all these things, you do a spectral decomposition of this R hat matrix. You isolate the eigenvalue lambda 1 of the equilibrium distribution, and V1 has component square root of pi I, which is the result of the similarity transformation between W and the symmetrized version. And then there are all the others, the sum over nu equals 2 to n eigenvalues, eigenvectors V nu and their transpose, so the outer product. And the point now is to know, if you think of a system which is irreducible, think of the giant component of a large network. So if you have, in case you have a random network, there are quite frequently sort of finite clusters and the giant infinite cluster in the thermodynamic limit. And we are really only interested in the giant cluster, because on a finite cluster, if you have a long walk, it will at best only explore the finite cluster, and then the search efficiency will be proportional to n, but the proportionality constant will of course vanish, and the little n goes to infinity limit. So we should concentrate on the giant cluster. And De Bacco, Solich, and Majumdar actually concentrated on the giant cluster by actually doing this entire theory on finite networks, which they took large, and solving the message passes equations by extracting the giant component of these large networks and doing it numerically. So, and we will also do that, but we'll also try to establish what can be done in the limit where the network becomes large. Now, if we are in the irreducible situation, then the lambda nu for nu not equals 1 are all in absolute value less than 1, and so 1 minus z lambda nu in the z goes to 1 limit will be something which remains finite, whereas the first term diverges. So we are really only interested in the first term in the thermodynamic limit. You can, and then the SI of Z, because it involves Gij, which you can express in this form. The SI of Z can be actually, you can convince yourself that you can write it as this. There is the non-diagonal element V
v1i, v1j divided by 1 over 1 minus z, which is happening here. And there is still the diagonal element of this resolvent evaluated in the limit z equals 1, which we have to do. And that is the non-trivial part. So the rest is sitting in the eigenvectors, and let's see how we do that. So as we noticed, the last equation has this 1 over 1 minus z squared divergence, and that actually, if you think of it, if you have an asymptotic behavior as I of n goes like dn proportional to n for n large, that is actually what translates into a 1 minus z squared divergence. So we can read off actually the b as this sum, and you should think of this sum actually as evaluated in the large n limit. So this rjj should be considered as the limit n goes to infinity, eventually the limit z goes to 1 in that order of the diagonal part of this transformed resolvent. So so this was for network exploration, and it is trivial to generalize this to search efficiency because the hij just multiplied with the psi j, and there is a contribution if there is a site hidden on it or not. So that's really a trivial generalization. I should not be particularly proud of that idea. But these still need to be evaluated. For these we have explicit forms, and since we have a factor y with it, which itself diverges with n, the right-hand side will be evaluated in the end by appeal to the law of large numbers. If these distributions of diagonal elements of this resolvent exists, and averages of all these exist, we'll eventually end up with an equation which is a sum of averages. Now let's briefly talk about this hide and seek aspect of the thing. So what we will do in the end is to evaluate search efficiencies for different hiding strategies. And hiding strategies are characterized by a function h of k. So we assume that there isn't, so the probability of an item to be hidden on a site with degree k is some proportionality constant times a function, k-dependent function h of k, h for hiding strategy, divided by the average of h over the degree distribution. So that means on a fraction, a row h of sites is covered, but it's covered in a degree biased fashion. And we will be looking at these kind of, this is just to show you our conventions and parameterization. So power law hiding, power law searching, exponential hiding, exponential searching, and logarithmic hiding, logarithmic. So these are sort of the basic families, and then you could of course have unbiased hiding and unbiased searching by taking alpha and beta equals 0. So that the unbiased random walk and the unbiased hiding strategy are concerned. And then you could think of, given there is a hiding strategy, you investigate the parameters of a search strategy and see where it's maximal, so where the efficiency is maximal. And then you can think of experiments like have matched families, so pitch exponential search against exponential hiding, or pitch the power law search against exponential hiding. So there will be matched families and unmatched families. And intuition would have it that matched families are probably the best member of a matched family is probably better than the best member of an unmatched family. And this is what we will actually find. Okay, let's evaluate these search efficiencies. Here they are. So the non-trivial bit is the evaluation of the RJJ, and they require the JJ element of these inverse matrices. And the way in which we do that, we follow basically an idea of Edwards and Jones, who used it in the replica context. And actually, I followed mainly Edwards and Jones when I did my first calculation of sparse matrix spectra. You can interpret this as the elements of R hat as covariances of a multivariate Gaussian. And the Gaussian is actually of this form. It has R hat of -1, so R hat is the covariance matrix. And this is a zero mean Gaussian, so this is what you have. So that's what they did, and Edwards and Jones evaluated the trace by taking, basically evaluating a suitable derivative of log z. So that, and then, so disordered systems, you do replica and all that, but it's actually simpler to do it via cavity ideas. So in order to do that, the first thing is we have in R, we have this, in the matrix elements, we have this combination of xi over square root gamma I. And I do this rescaling of the R elements in this form, which normally gets me on the diagonal part an xi squared gamma I. And I symmetrize that in order to have a manifestly symmetric quadratic form here. So this is now a symmetric quadratic form, and in order to evaluate the diagonal elements, I only need single side variances of this multivariate Gaussian distribution. So just to make it very formal, I have some statistical physics system which contains binary interactions, and I could in principle do it for all sorts of binary interactions. We'll find that. So this is the task. We have a multivariate distribution which depends on a pair interaction only, and we have to evaluate single side values. And this is how you do it. So this is a brief explanation of the cavity method. So for any I can evaluate h of x, including the terms which have I in them. That's the sum over j b of xi xj. This is the terms which depend on I, and the rest is which doesn't. So you have the terms which depend on I. This is any single side term which depends only on I, plus everything which has I as links in it, and that's the first sum. Is actually this little star of degree 3 here, and then there is the rest, which I call hi. So this I is for the cavity. The side I has disappeared. This is the x's which are neighboring on I, and these are further away. Okay. So, and the full system is described by h, and the cavity graph is described by this reduced Hamiltonian, which has I and all links connected to I with reduced from it. And you see if we think of this graph to be a tree, then after taking the central side out, we have decomposed the system into independent subsystems, and that is the core of the goes further away. And if we do the red integration first, they involve only this cavity Hamiltonian, and that then becomes something which is a cavity marginal, a joint cavity marginal. So our single side marginal is expressed as an integral over the degrees neighboring on this side that we're interested in, times this exponential function which brilliant, times this exponential function which depends only on the things which interact directly with I, and then the joint distribution of the cavity marginals. So that's the structure of it. And here now it comes, if we are on a tree, this factorization is exact. If we are on a tree-like graph where loops become long, this becomes asymptotically exact. And if we think of finite mean degree random graphs, the loops are like log n diverges in the infinite system, so this will be arbitrarily precise in the log system. So now we have an expression of single-site marginals in terms of integrals, basically integrals over cavity marginals. You can repeat the argument for the cavity marginals and you find that the single-site cavity marginal at site j is again a multiple integral over cavity marginals at the sites L neighboring on j but the site j is real. And here is now a system, the star equation, is a system of self-consistency equations for these objects, cavity. Now, you can convince yourself that with the V, which is of this form, which we have seen before, this equation, this set of equation, this V is quadratic. So this is a quadratic function of xj and xl. If this is a quadratic function of xl, then obviously this system of equations solved self-consistently by Gauss. And so what I will assume, assuming that the Pj are Gaussians with inverse cavity variance omega ji, I can translate these cavity equations into a set of self-consistency equations for these numbers. Rather than having functions, I just have inverse cavity variance. And it turns out that if you have a large graph, you generate it, you can solve this iteratively for given large instances. It's a very, very quick algorithm. We haven't come across cases where we didn't find a solution by forward iteration. So you insert random guesses for the omega for the initial value, you iterate forward in an asynchronous fashion and converges very rapidly. And we have the single-site marginals. The equation was of the same type. You remember we have, for the cavity marginals, we have this exclusion condition, which we don't have in the single-site marginals. So the single-site marginals have the similar structure. We have a solution of these guys. We've obtained the solution for the omega JL, and so we will know the omega I once we have solved the cavity marginals. And if we insert everything, this is our final result for the search efficiency, which is just the sum over the omega I. And then, I'm not sure whether this appears on the next. Yes. So this is now what does the show on finite instances. We could run it, generate graph, put psi i's equals 1 on it, solve this system. Once the system is solved, we have the omega I. Once the omega I is solved, we have the search efficiency, actually the prefactor in this. Now the thermodynamic limit. What you could do, and I'm referring to this equation, in the thermodynamic limit you could think of this is just a stochastic recursion between a set of random variables on the mass. So what you would do is self-consistently estimate, assuming that there is a distribution of these guys, you try to estimate self-consistently the distribution if these guys satisfy this equation. It can be written down. There is just one hitch, and that is one thing. The structure of this requires that we need degree-dependent families because the central site, again, sorry, this is not well designed. This omega j, the degree of the central vertex appears here, whereas this these are distributions. So we have the degree of the central vertex in the thing. So this is why we need, because of this side randomness, we actually need, for an ensemble of, so we need degree-dependent families of such distributions. So that complicates the system problem a bit. But the more subtle thing is we actually need to do that to project on the giant component. You could argue, if you just run this without thinking, then the contribution of the b's which come from the finite component will be simply 0. So the b that you compute will make this error, and you just divide by the fraction of sites in the giant cluster and you're fine. And this is what we did initially, and it turns out that it's wrong. And why? And the reason is very subtle. In one part of the Debacco-Majumdar-Solich argument, they used the fact that the Perron-Frobenius eigenvector is unique. And that is really only the case if the system is irreducible. Now, in a random graph ensemble where you have many clusters, you can have all kinds of linear combinations, and it's no longer the case, and that distorts the result in an unpredictable way. So we have to find a way out of that. And actually, a couple of years ago, I did this for random matrix spectra. So you can really do random matrix spectra restricted to the giant cluster. And why would that be interesting? You want to eliminate all the trivial effects of finite clusters. So I'm very proud of this. It's not much seen, so have a look at that. It's really a nice little short paper. So what we have to do is to combine the self-consistency problem with the self-consistency problem of the percolation problem. So what's percolation? I introduce an indicator variable ni, which is 1, if site I is on the giant cluster. So site I is on the giant cluster if at least one of its neighbors is on the giant cluster in a graph which does not contain I. And that's this equation. You have 1 minus the product over the neighbors, and if any one of them is 1, meaning it's on the giant cluster, then this product is 0 and the result is 1. If they are all 0, then the product will be 0. So that's the expression of the indicator variable to be on the giant cluster in terms of the cavity indicator variables of the neighbors. And the cavity indicator variables of the neighbors are now in a similar fashion. Now this is again a system of equations which you could think of as stochastic recursions for these random variables, binary variables, 0, 1. And what we have to do is take the combination of the stochastic recursion for one set of variables and the other simultaneously. And I will not go into huge detail. I just write down the results. So I'm having a k-dependent families. K is the degree. And you recognize here the structure of our equation for the omega tildes. If we have k, if we have a degree k side, there are k minus 1 neighbors on the cavity side. This was actually the structure if k is the degree of the central side. So that was the star equation on a single instance, this side of thing. So the star equations of the single instance some pages back. And now what we do is the following. If we have a degree k cavity side, we sum over k minus 1 neighbors. Their degrees are picked with these probabilities. K over Cp of k is the probability to connect to a side k. And then we pick k minus 1 entries from this joint distribution of the omegas and the cavity omegas and the cavity ends, compute this combination and assign this value of omega to the new value. And then we do exactly the cavity calculation side of thing. We compute 1 minus the product of these guys and assign the value. Now this is a horrible set of equations, of course. It's highly nonlinear. But there's a very, very efficient stochastic line of attack for this. That's population dynamics. So what you do is you pick these k's according to this distribution. You pick k. You represent this distribution by a large family of values. You initialize that randomly, and then what you do, you pick k news according to these values. You pick omega news and n news according to these distributions. And then you recompute these values and you replace a random number of the k's population with that. You iterate that and converges. Once you have convergence, you can get the k-dependent family of the margins with a similar value. Okay, so that can be done very efficiently. And then in the thermodynamic limit, what you find is that the B is actually a sum over the degree distribution conditioned on the giant cluster, which has this form. The conditional expectation of the omegas over the pi distribution, the pi k distribution on the giant cluster, the conditional expectation of the k, of the psi conditioned on k, you sum that, and there's a normalization constant which you can also compute. This rho tilde, I don't know whether it's written here, the rho tilde is the probability that a random neighbor of a randomly chosen site is on the giant cluster in the thermodynamic limit. For that you have a self-consistency problem. So everything can be done, and done really with, so I should talk about results. So here is just a simulation of a couple of graphs of size. Now there should be 6,000. You pick the giant cluster, 98% of the guys are in the giant cluster roughly. You analyze that using simulation, and you find that the number of sites that you find is actually Bn for a range of n. So, and from that you can, so that was done, and you extracted from simulations with really fairly high precision. So this is just to show that the phenomenology is right. Here we check network exploration on the left-hand side, comparing simulations blue with the cavity results in red underneath, and they are on top of each other, so there's basically no difference in this thing. And again, this 600 should actually be a 6,000 consistently. So this is for network exploration. For a degree biased random walk with power law degree bias as a function of this power, and what you see, if the power is very negative, the exploration efficiency is bad because it picks low degree sites, so it will predominantly locate itself at the ends of bending chains. And if the degree is, so if the power is somewhat intermediate, it's very good, and then it decreases because then it starts to concentrate on large degree sites, and there are not so many in this arbitrary graph, so it starts becoming inefficient again. So we find there's an optimal value which is much larger than badly chosen values. That's the optimal value is not 0. The optimal value is close to 1. So an unbiased random walk is not the best way to explore the graph. And the right-hand side is search efficiency for a hiding strategy, which is degree biased with k, and the maximum is approximately k squared. So again, matching the hiding strategy is not the best thing to do. And what we did here is the hiding fraction is 0.025. In the optimum, it's larger than slightly larger, so you find actually a little bit more than you would expect to find given the fraction of sites which are occupied. So this is now comparing the infinite system limit with again 6,000 networks, and here it's thermodynamic limit versus cavity recursion on a single instance, and basically the same results. Here is network exploration, and here is search for the same parameters. This is arbitrary. So these two sets of results simply say the cavity is really good in moderate-sized networks to reproduce the simulations, and it's for these size networks, the average over many single instance realization is equivalent to what you see in the thermodynamic limit. This is now pitching several hide and seek strategies against each other. For instance, power law search on the left panel is pitched against power law hiding for various beta. And if beta increases, there is a large heterogeneity on the degrees of the sites where you find items. And this row H is still 0.025, and you see that you have almost 0.035. So pitching it well, of course you can do for negative beta. This is what you get. You will never get. So from the point of the hider, the searcher will never do well if you take very negative beta. From the point of, and this is the best thing that the seeker can do. So there is in these results even some results from the game theory aspect of it. But from the point of view of from the seeker, if the hider is stupid enough to put it on high degree nodes, which you can argue even from an unbiased random walk point of view, if you want to hide things, you should not hide it in the room which you randomly enter many times if you just make random. But what you see is that the heterogeneity can be exploited. And the right panel is the same for exponential search strategy, again for various power law strategies. Same type of results. And this is a case where we do logarithmic hiding, where beta equals 0 is actually meant to be unbiased hiding. It's slightly unsystematic. Again, you see for small betas, this is very weakly dependent on beta, the optimum, but if beta becomes very, very large, then you get sort of decent efficiencies. And the right panel is logarithmic search against logarithmic hiding. And what you see is actually the matched strategies are always slightly better than the unmatched strategies. Here is briefly a result on the influence of graph structure. So we took graphs which have roughly degree 4. The Adler-Shreni graph with degree 4. There's a random regular graph with this inverse gamma power, which has close to 4 degree. Then the random regular graph, there cannot be a degree biased effect of degree bias in a random regular graph. This is the result for the random regular graph. The best strategy for Adler-Shreni graph is better than that. The best strategy for the scale-free graph is better than that. And this is a real-world network. And I forgot to write down what the mean degree was. It was also close to this value. Slightly higher, that might affect. But this is a file sharing network, so a real-world network where you, and this is network exploration. And I think, yes, I'm almost done. This is just a non-backtracking approximation. You can think of, if you have a large mean degree network, a random walk is always an automatic drift, because you have, on the degree k side, there are k minus 1 guys to go in different directions, and only 1 to go back. And if you now assume, you always see something new when you don't trace your argument. You can do an analytic approximation. And this is the analytic approximation for C equals 4, the true result and the approximation. And this is the degree 8, Adler-Shreni, the true result and the analytic approximation. And this is a fairly straightforward thing, much simpler than all our massive theory, which, as we see, does well both for network exploration and search. And I should really finish. And this is my summary. So we've evaluated network exploration and search for biased random walkers. using cavity method for large single instances and the thermodynamic limit, there's this non-trivial thing of projection onto the giant cluster, which you might find useful in other contexts that it can be done. Degree bias in search can significantly enhance the search efficiencies, and degree bias can also exploit heterogeneity of the network. So if you have a scale-free network, the right bias is really and optimal search efficiency is larger than the fraction of sites on the networks is clearly possible with sufficient heterogeneity. And there's excellent agreement. There are a lot of things to do. So thank you for your attention.
Thank you very much. Time for questions, comments. Anybody use also the microphones?
Actually, I have two questions, if the chairman allows.
Please.
The first one is, this class of planar graphs, they are called planar maps, the simplest of which is planar triangulation.
Yes.
By construction, they are two-dimensional.
Yes.
But they are known to have Hausdorff dimension or fractal dimension 4.
Yes.
And I'm just wondering whether they are recursive, like what would be suggested by the Hausdorff dimension 4, which is larger than 3,
Yes.
or rather by, local structure. Just I know, for example, that Hausdorff dimension is 4, but spectral dimension is 2.
Yes, and that's in that case there would be this. I think the spectral dimension is what matters in search efficiency. It has been done on some of these self-similar graphs. I don't know the results offhand, but I can point you to the literature if you're interested. So I don't know the figures, but the second, in order to have efficiency proportional to n, so this proportional to n results, you need the spectral dimension to be larger than 2.
Okay, that answers my question.
Yes.
The second question is related to something which is called maximal entropy random walk.
Yes,
it is a biased random walk, but the bias is not coming from the nearest neighborhood, but from the second, third, and so on, from all generations.
Yes, I remember that you've written something on that some years back, but I haven't looked at it in this context. So
I think that it will be bad in this respect, that it will just localize on sites which have high degree, and in a sense they will not explode.
That happens here as well. If you sort of have a very strong degree bias, you find localization transitions.
So okay.
You will hit those issues. So there is similarity. I haven't looked in detail at sort of matching this quantitatively. I'm aware of what you've done some years back, but I haven't.
Suppose you have some real-world network like the protein network, and you want to get some idea what class of network it belongs.
Yes.
So you let some chemical to explore it.
Yes.
In which sense this methodology may help us to get idea what kind of network it is? Scale-free or small world or?
Well, I mean, if you say you see so many different sites, the problem is if you take a degree biased walk, you always look around you and then you look around you what the degrees of your neighbors is. That's a little bit of an information which you may not necessarily have, but assume that you have it. You might actually be able to, in the configuration model class, you might actually be able to get good approximations for the degree distribution. If you assume some correlations between degrees of neighboring sites, you might even be able to do that. So having theory for degree bias at your disposal, I think it could improve your results because you could play with it and see the different results. I think for network sort of tomography, if you like, this could also be a useful tool. We have not looked at it in detail, because also you would really need to have a better control of this, and we don't know how to do it within this theoretical framework yet.
No further questions. So let us thank Reimer again.